Now that we've looked at some basics of both Excel and MATLAB, we move into some applications. First one we'll talk about is graphing. And creating a graph is an important skill. It's a communication skill because with a graph you can visualize some large data sets that are very difficult to do with just a table of numbers. You can look for trends in the data and for cause and effect relationships. So let's look at Excel first. In Excel, a graph is just called a chart. And there's a lot of kinds of graphs that you can make in Excel, but the one that we're most interested in, the one that we use the most, is a scatter chart or the XY graph. And within that you can show data markers, straight lines, smooth lines, etc. And they also create bubble charts there, but we're not going to talk about those. So again, the scatter plot or the XY plot, it's the most important kind of graph that we use in engineering. And with that, we plot a dependent variable against an independent variable. So the independent variable, usually called x, will be on the horizontal axis, the dependent on the vertical axis. And we say that we're plotting y versus x, or you can think of it, the dependent variable as a function of the independent variable. And sometimes you can plot more than one on the same axis, more than one dependent variable. So for example, here's the graph of sine of an angle from 0 to 360 degrees. Independent variable in this case is the angle, and the dependent variable is the sine. For comparison, we could show the sine and the cosine on the same graph. And you notice that we've added a legend here so we can tell which is which. Now, when you plot an equation or theoretical values on a graph, you should do it with smooth curves, because the points that you pick to make the curve are not significant. You don't show those point markers. On the other hand, if you're plotting measured data, then you do want to show those markers. So here's an example from Mechanics of Materials lab where we've done tests and we found these 4 data points. So again, the data points are important points, and so we do want to show those with markers. Now, almost always, though, we add some sort of a line. Sometimes you just connect the straight line segments. You add a theory curve or a fit line, which we'll call a trend line. We'll talk a little bit more about curve fitting in just a little bit. So in this case, we've looked at the theoretical versus the measured. And again, very quickly we can visualize that our measured data maps against the theoretical data pretty well. So line graphs are used when you have categorical information on the x-axis. So example, months, days of the week. In this case, it's monthly sales plotted against the month. And so again, with those categories, January, February, March, the points are plotted always at equal intervals. So you don't really want to do that with numerical data as your independent variable. Always want to use a scatter graph and not a line graph. And especially this is true if you have data points that are not equally spaced. Well, a line graph is going to space those points equally anyway, and so your graph won't be correctly proportional. So again, most of the time in engineering, we're plotting x and y data pairs, and so we always want to use a scatter graph and not a line graph. So a couple things about graphing practices in general. Again, it's a really good communication tool, so you want to be able to communicate well. This is not a very good graph right here. Usually want a title, and either above or below the graph. And a lot of times in a paper you'll have a figure number and a description, so that'll go below the graph. Always label the axes and always include units. You should just have a plain background. Grid lines are really good, but and by the way, the default now in Excel is for these gray grid lines, which blend into the background pretty well, and that's a pretty good choice. Remember that in this case we're plotting equations, so no data markers for this. And while you may be printing in color, always remember that if the graph's going to be printed in black and white, you want to be able to distinguish those curves. So in this case we've used a solid line and a dashed line. And there's the finished graph, which looks pretty good. Now, a couple of types of equations that we might want to plot. This is an exponential equation. Y is equal to e to the 1.5x. And so when we plot that on regular linear axes, you'll see how that curve looks. And if we plot it a little further, you'll see it goes up at a very high rate. If we plot that as a semi-log graph, that is, the y-axis is logarithmic and the x-axis is still linear, you can see that this plots as a straight line. By contrast, let's look at a power equation. For in this case, our independent variable r is raised to a power. Now, once again, if we plot this a little further, we'll see that the value increases very quickly, so it's hard to interpolate values down on the lower end. But if we plot both axes with logarithmic scales, then you'll see that, once again, we plot as a straight line. So always remember this. Exponential equation is one where the independent variable is part of the exponent. And for that, you want to use semi-log axes for that to plot on a straight line. By contrast, a power equation is when the independent variable is raised to a power. And that plots as a straight line on log-log axes. Now sometimes we want to fit a line or a curve that fits the data points that we have. And so here are just arbitrarily 3 data points. And so we might ask, how do we best fit that data? And so that's done with what's called least squares. So it looks at the square of the difference between the theoretical line and the actual data point. And by squaring it, it kind of gives equal weight to points that are above or below the actual line. So here's that example. There's our 3 points, and so we want to fit a line in there that minimizes the sum of those squared differences. The correlation coefficient, which we can also have printed out in Excel, shows how closely the line fits to the data. And a value of exactly 1 means it's a perfect fit. And you can see we took our simple example there and changed that second point so that all of them are indeed on a straight line. And when we do the curve fit, the r-squared value comes out to be exactly 1. Now both Excel and MATLAB can do that best fit. In addition to linear, you can do other types of curve fits, polynomials, exponentials, etc. And again, the correlation coefficient, in the case we did one where we looked at the deflection of a linear spring, we really expect that that should fit a linear line, and so we should get an r-squared value pretty close to 1. In another example we looked at, we said, okay, what if we look at final exam scores versus homework average? We know that there's not a perfect correlation to do for that, and so our r-squared value will come out to be less than 1, which is to be expected. So as a summary, we put trend lines to fit a straight line or a curve to the measured data point. That correlation coefficient, the r-squared value, tells us how closely the curve fits the data. If it's the closer you are to 1, the better the fit. But we do say that, the type of curve should be consistent with the nature of the problem. You don't always just want to pick, say, a 6th order polynomial because it fits the data best. Something like a linear spring test, we expect that to be linear, so we put a linear fit in there. On the other hand, things like temperature decay, population growth, those tend to be exponential, and so we'd use an exponential fit for those. Within MATLAB, to make a plot, it's pretty easy. There's a command just called plot, and if we have 2 arrays, x and y, then it just plots those points individually. There's also, for a MATLAB function, we can use the fplot command. So starting out with plot, x and y have to be 2 one-dimensional arrays, and of course they have to be the same size because we're plotting pairs of data. If there's more than one, then you can do it like this, x1, y1, x2, and y2, and those will be on the same axes. Another way that you can plot 2 curves on the same graph is to use the hold command. So when you type in hold on, then the next data that you plot will go onto the plot that's currently open. A figure command simply will open up a new plot window instead of overwriting the existing plot. Now, if we look at a function, here's a function that we did for the temperature of a ball bearing as a function of time. If I use the fplot command, then you can see the way to do that is fplot, and then in parentheses, the name of the function beginning with the and sign. Then we put the range. If we don't put a range, it automatically goes from -5 to 5. In this case, we want to go from 0 to 300 seconds, and you see the curve that's produced. And of course, then we can edit it to show the grid, to show the axes labels, etc.